In our last topic for the unit, we're going to be looking at something called angles of elevation and angles of depression. Really, though, these are just ways to describe which angle we're looking at in a diagram from the perspective of, somebody in a real life situation. So if you think about the words, elevation, well, it means you're going up. You've talked about elevation of like mountains, how high somebody is up compared to sea level. And so angle of depression would be looking down. So angle of elevation, in the first example, we have a person looking up at the top of a lighthouse. So the angle of elevation is how far they would have to arc or tilt their head to be able to see up, if they're just looking straight ahead, they're not moving their eyes. Angle of depression is how far does somebody have to look down, or how far do they have to angle their vision down to see something. We may also have problems where we have to take into account somebody's height. So again, like in the first, sample diagram, if that person has, some amount of height, that perspective has some amount of height, we need to take that into account when we're talking about the object that they're looking at the top of. So let's see how this is set up in some different scenarios, but we're still going to use the same solving techniques that we have throughout the last few lessons. So mostly trigonometry. We might possibly come across something with Pythagorean theorem, but most of these problems do relate to trigonometry or sine, cosine, and tangent somehow. So let's jump in. The biggest thing is just making sure you understand the situation and can draw and label your diagram. So in example 1, we're going to find the angle of elevation of the sun when a 1 or 12.5 meter tall telephone pole casts an 18 meter long shadow. So our angle of elevation is down where this question mark is. I'm going to go ahead and relabel that as X. And if we were thinking from the perspective of somebody sitting on the ground, or maybe even a little bug down on the ground, because we're not taking into account any extra height on this, how far would they have to look up to see the top of the telephone pole if they're standing at the end of that shadow? So this is just a trig problem again, though. Identify the angle that you're using. In this case, we're going to have to solve for X. Our 12.5 is our opposite side, and our 18 is our adjacent side. And so what ratio does that use again? Again, if you need to, over in the margin, always write down your mnemonic. So, toa. And so opposite and adjacent, well, that one's going to use our tangent ratio. So tan or tangent of our angle X, our angle of elevation, equals our opposite 12.5 divided by our adjacent 18. And so just like in our last lesson where we're solving for the missing angle in a right triangle, we have to use our inverse to be able to switch our spots to get the X by itself. So this is really tan inverse of 12.5 over 18 equals our angle X. And all we need to do is plug that in the calculator. So again, going back to your Desmos calculator, or you can use the Schoology calculator if you open the scientific calculators link, or if you have a TI calculator, you can use that as well. But tan inverse of 12.5 divided by 18, I'm getting out approximately 34 point. Let's see, it doesn't have, how far we have to round. So when in doubt, I always go to 4 decimal places just to make sure that I'm super accurate. So I'm getting X is approximately equal to 34.7778 degrees. Alrighty, again, just a trig problem, same thing as what we did last lesson. So let's look at number 2. Number 2 is a little bit different. So you'll notice with this one, we have a person in the diagram. They're looking at the top of a water tower, but they've made special note of their height. So we need to take that into account when we're solving this problem. The biggest thing is being able to find our right triangle in that scenario. So let's read through the problem, make sure we have everything labeled. So if someone whose eyes are 5 feet above the ground, so that's our 5-foot person in the diagram, they're standing 100 feet away from a water tower, and they have to angle their head up by 52 degrees to see the top. How tall is the water tower? And so looking at the diagram, I actually have 2 pieces to it. So I have, let me change over to red. I do have a right triangle in here. So there's my right triangle. I know the base is still going to be 100 feet. because it doesn't matter if we're from the perspective of her eye level or the ground. We're still 100 feet away from the water tower. And we have our 52 degrees. I could absolutely solve for that height of the right triangle. But ultimately, is that going to give us our final answer? Well, we would also then need to add in that extra 5 feet from her perspective on this problem. So let's first solve for x, and then we can deal with the extra 5 feet. So again, using 52 degrees, we have our x, which is actually our opposite side, and we have our 100, which is our adjacent side. This is another tangent problem. So tan of our angle, 52 degrees, equals our opposite over adjacent. And this is like what we did in lesson 7C, where we were solving for missing sides. I don't have to do my switcheroo on this one. I don't have to try to get an x out of the angle position, but I do need to deal with that 100, get that out of the denominator of the fraction so I can work the problem. Okay, so multiply both sides by 100. Then that takes care of our 100. And we have 100 tan 52 degrees is going to equal our x. And so plugging that into the calculator, I'm getting that that is approximately 100 tan 52, approximately 127.9942 if I round. Okay, but is that the answer to the problem? Unfortunately, that is only the length of the x. So just from the right triangle. To find the final length, let me change back over to purple. To find this final length, I need to take that x and I need to add the additional 5 feet that we have to account for from that person's perspective. So really, the water tower is 127.9942 plus 5 feet. And so if I add 5, I'm looking at 132.9942 feet. And again, if this was a problem where we wanted to round to the nearest foot, then we would say 133 feet. But notice too, I'm also using feet, my measurement, my units of my measurement in my final answer, because I want to make sure, am I referring to a side or am I referring to an angle? Always keep your units in there. Alrighty, example 3. This one doesn't have a diagram, so we're going to have to draw one. A pilot in a helicopter spots a landing pad below. If the angle of depression is 73 degrees and the horizontal distance to the pad is 1,200 feet, what is the altitude of the helicopter? So, I haven't actually seen a helicopter land unless you count seeing it in movies. And so we have our helicopter, and I am not an artist. So here's our helicopter with the little thing, and we've got a person that's in the front of the helicopter. Again, I'm stick figure artist. I am not an artist. But somebody sitting in the cockpit of a helicopter is not going to be able to see directly below them. They're going to have to look down out of the cockpit to see the landing pad. So let's call that LP for landing pad. And so I can actually go ahead and create a right triangle by going straight down and straight over. Okay, let's reread. The pilot in a helicopter spots a landing pad below. The angle of depression is 73 degrees. So if you imagine somebody in the helicopter, they have to angle their vision down. And they're saying this is by 73 degrees. So if they looked straight out versus angling their vision down, they have 73 degrees. However, that's not in the triangle. So there's 2 ways that I could deal with this. What kind of angle do I have to have between the vertical distance and the horizontal line of sight for the helicopter pilot if he was looking straight out? Well, those would add up to 90 degrees. So to find the angle that's inside the triangle, I could just subtract from 90 degrees. But also too, think about this line of sight here. How does that compare to the line along the ground? Well, those lines would be parallel, so I could also say, well, whatever this angle of angle of depression is up here, if I use my whole idea of parallel lines, like what we looked at in Unit 3, parallel and perpendicular lines, I could use my alternate interior angle and also label the angle of elevation. And in fact, your angle of elevation and your angle of depression are always going to be parallel to each other. So let me go back up to our sample diagrams real quick before we finish this. So look at, our middle example, our lifeguard that's sitting up in the seat so they can see somebody at water level more easily. Their angle of depression here is actually the same angle as the elevation of somebody that's swimming looking up at the top of that lifeguard tower. So you can always label those out just using our parallel line ideas. And we could approach the problem either way, but that's how I tend to label my diagrams. So let's go back down to our problem. So I have my 73 degrees. Okay, it says angle of depression 73 degrees. We got that. The horizontal distance to the pad is 1,200 feet. So that's going to be our horizontal distance, 1,200 feet. What is the altitude of the helicopter? Well, what does altitude mean? Think about if you've ever been in a plane, the pilot announces we're cruising at an altitude of 32,000 feet. That's how high they are up in the air. So let's call that X. That's what we want to solve for. And now we have our right triangle. Compared to our 73, our X is our opposite. Our 1,200 is our adjacent. And we're using, wait a second, we're using tangent again. Actually, let me do that. It's working on the page break a little weird. There we go. So that's our ADJ. We're using tangent again. So tangent of 73 degrees equals opposite over adjacent. And we have our opposite labeled as X and our adjacent labeled as 1,200. So same as before, I'm going to multiply both sides by 1,200 to clear my fraction. Alrighty, so I have 1,200 tan 73 degrees equals X. And so that means our X, our height that we're looking for, let's see, 1,200 tan 73, 3925. Again, it doesn't ask us to round to any specific place, so I'm going to use 4 decimal places, 0, 2, 3, 1 feet. And if you think about that, that's appropriate for the problem. The helicopter is going to be quite high up in the air. 1 mile is 5,280 feet, so they're less than a mile in the air. So yeah, they're a ways away. However, if visibility is good, then, if they've got that big red landing pad to look for, then they may be able to see that pinpoint pretty easily, hopefully. Alrighty, a few more examples. Here we go, example number 4. So in 2005, this is an old problem. When discussing the proposed border wall between the United States and Mexico, the Arizona governor, Janet Napolitano, you show me a 50-foot wall, I'll show you a 51-foot ladder. So while the scenario, not that great, we can actually think about, well, mechanically, would that make sense? If I have a 50-foot ladder, or 51-foot ladder, is that going to be enough to get to the top of a 50-foot wall? So do you think that's going to be enough? Well, my diagram's not very accurate. 51 feet is not much longer than 50 feet. So that means that ladder is going to be very, very close to the ground. And so let's see, let's do parts B and C and see if we can get some, better answer for this. So in part B, it states OSHA requirements. Now, if you haven't heard of that, OSHA stands for Occupational Safety and Health Association. And so there are standards that are out there in the workplace to make sure that, people are safe in doing their jobs. And so specifically, OSHA requirements state that we've got to have an angle of 75.5 degrees with the horizontal. So that's this angle, basically our angle of elevation. We want to have the ladder far enough out from the wall that it has good support, but not far enough out that it's not going to be very stable. This is why usually if you're getting up on, a simple ladder like against the side of the house, you should always have a spotter to make sure that the base of the ladder doesn't move. And so we need to see, is that 51-foot ladder going to meet that requirement in that scenario? So let's solve for that angle and see what happens. So in our diagram, our 50-foot wall, that's basically our opposite side. Our 51 is our hypotenuse. So what should we use in that scenario? Yeah, we should use sine. So sine of, I'm going to go ahead and say x for our angle, equals 50 over 51. And so this is where we're doing the switcheroo. So we need to do sine inverse of 50 over 51 equals x degrees. And so plug that in and see what we get. So sine inverse 50, 51, that gives us 78.6351 degrees. That is too large. So that means that this angle that we're looking at, bottom of the triangle, we would need to make that smaller. We would need to pull the base of that ladder out to be a little bit safer. So 51 feet is just not going to cut it. Okay, so how long of a ladder would we need to meet those OSHA requirements? So what we're going to do is change our diagram. So we still have, we're trying to get to the top of 50 feet. Our angle needs to be 78.6, going back to our OSHA standards, 75.5 degrees. And we need to figure out what our length of our ladder is. Let's call this y so we're not using the same variable. So we're still going to set up a sine problem. So sine, but now we have our angle, 75.5 degrees, equals opposite over hypotenuse, 50 over y. So we need to get the y by itself. Again, we always start by clearing our fraction. So y sine 75 degrees, or 75.5 degrees. We still need to get the y by itself. So we're going to divide both sides by sine of 75.5 degrees. And so this would then yield that y is equal to 50 over sine of 75.5 degrees. Plugging that in, sine 75.5. So 51.6450. So we wouldn't need to make the ladder much longer, but we would want to safely do that. Now, obviously, that scenario is completely inappropriate, but serves the idea that, people need to think before they speak. So A, shouldn't take geometry, and B, she definitely was not in the right headspace. Alrighty, so I want you to go ahead and do the you try problems. So at this point, if you're feeling comfortable with these problems, go ahead and stop the video, and then you can check out your results on the completed organizer. If you're not feeling comfortable with these quite yet, I'm going to go ahead and run through these in a quick moment. All right, so let's try the extra you try examples if you still weren't comfortable with this. So again, both of these need a diagram. So in both cases, we're going to draw a right triangle and then label our information that we need. So a lifeguard is sitting on a platform. It's like that sample diagram that we had up at the top. So here's our right triangle. Our lifeguard is going to be sitting up at the top at the point. So they are 8 feet above the ground. The angle of depression to the swimmer down in the water. So here's our swimmer. Angle of depression means they're angling their vision down. And we need to know how far away is the swimmer from the lifeguard. Now, when we're measuring that distance, we actually want to measure along the horizontal. So let's label that as our x and then solve this out. What do we need to do first, though? Can I use the 18 directly? Yeah, I want to relabel that 18 or label another angle. Again, I tend to go for the parallel line angle pair, so I go for my alternate interior angle, and that's what I'm going to use. So here's our angle measure. Compared to that, we have our opposite side with 8 and our adjacent side with x. And we have yet another tangent problem. And you've probably noticed that these are happening pretty often because it's a lot easier to measure a straight horizontal line or a straight vertical line than it is to measure something diagonally. And so that's why we tend to use tangent a lot more often in these application problems. So we have tangent of 18 degrees equals our opposite 8 over our adjacent x. We're going to have to do the same thing as we did before, clear out our x or clear out our fraction. So x tan of 18 equals 8, but we still have to get the x by himself. So divide by tan of 18 degrees, divide by tan of 18 degrees. That clears the tangent of 18 out from the left-hand side. So x is equal to 8 divided by tangent of 18 degrees. And then we just plug that in the calculator. 8 divided by tan of 18, 24.6215 feet. So the swimmer is almost 25 feet away from the lifeguard. And that's why lifeguards sit in those taller chairs. It gives them a better viewpoint, lets them see more of what's going on for safety reasons. Okay, number 6, Casey sights the top of an 84-foot tall lighthouse at an angle of elevation of 58 degrees. Hey, it's the first diagram that's all the way up at the top. So we have a person, again, stick figure person, that's okay. And they see the top of a lighthouse. So here's our lighthouse. And the angle of elevation is 58 degrees. Well, that's measured from, if we were doing horizontally, looking straight out, angle of elevation is how far they tilt their head up. And so this is one of those where we have to account for some extra height. Second sentence says, if Casey is 6 feet tall, how far is he standing from the base of the lighthouse? So this length here is 6, which means this is also 6. The lighthouse itself is 84 feet tall. So the full height here is 84 feet. So this one is almost looking backwards from the problem we did before. If you're seeing the right triangle, what extra length can we use to actually label a side on the right triangle? Well, we've got our 84 feet total. If we take away the 6 feet, that leaves us with a leftover 78 feet. And so that lets us label that vertical side of our right triangle. And now if we want to know how far he's standing away from the base of the lighthouse, we're just looking for that bottom length. And lo and behold, if we look at our values, compared to our angle of 58, 78 is our opposite, x is our adjacent. Yet again, it's a tangent problem. We see these most often. Alrighty, so tangent of 58 degrees equals 78 over x. It's another one where we have to clear our fraction. So multiply both sides by x. No more fraction. So tan 58 degrees times x equals 78. But x isn't by itself yet. So we need to divide both sides by tan 58 degrees. Tan 58 degrees. That cancels that out. And so now we are left with x equals 78 over tangent of 58 degrees. And plugging that in my calculator, 78 divided by tan 58 gives me approximately 48.7398 feet. So he's standing a little bit more than, or a little bit less than 49 feet away from the base. So again, we didn't have to add 6 to our overall height, but we did have to take that into account when labeling our diagram. As always, let me know if you have any questions and start working on your choose your own adventure practice. Again, if you have not yet done your lesson check from last class, that might actually be the better place to start. Let me know if you have any questions.